This is the 17.1 mini lesson. So previously you conducted trials for a simulation concerning guessing correct answers for multiple choice questions on a test. You will continue to explore the probability of guessing on tests. So we have George and Tristan are discussing the likelihood of correctly guessing the answer to a multiple choice question on a test if there were 5 choices for the answer choices instead of 4. They both assume that they have no idea what the correct answer is. They also assume that each multiple choice question has 5 possible answers, A, B, C, D, and E. So first it says to list the sample space. So the sample space is, we could guess an A, a B, a C, a D, or an E, and remember sample space is in the squiggly brackets. So what is the theoretical? So in theory, what should happen if the correct answer is an A? Well, A is 1 out of 5 choices. A B is 1 out of 5. C would be 1 out of 5. So would D. So would E. When solving a probability model or probability problem, it's helpful to construct a probability model. A probability model is a list of each possible outcome along with its probabilities. So right here, this is considered a probability model. It's just not a great way to display the data. So previously, when you listed all the outcomes of an event or completed a number array, so remember back to when we rolled 2 die and we said you could roll 1 first and then a 1 second. I could roll a 1 on the first die and a 2 on the second. And I could make a list, or I could make the array. That's where I had the 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And we made a table, and we said if I rolled a 1 and a 1, and let's say I'm doing the sum would be a 2. If I rolled a 2 and a 1, the sum would be a 3. So we've done lists like this. We've done number arrays like this. We were using probability models. Probability models are often shown in a table. So here they took the same data we have up here. If we changed all these to decimals, all of these equals 0.2 or 2/10. So they just wrote it out using the fractions. So what is the sum of the probabilities in the probability model? So again, remember, I would have to guess either A, B, C, D, or E. So it's certain that I'm guessing one of those. So the probability of all of these added together should equal 1 if you're certain, because you are certain to select one of those options. As with the sum of probabilities, a probability model will list all the outcomes, and all those outcomes would have to be greater than 0, but they're less than 1. So when I list each outcome separate, it falls in this range. The sum of all the probabilities is 1, which is, again, what we saw here. So why is the sum of the probabilities in a probability model always 1? So if we think about it, the sum is always 1 because the probability model lists every possible outcome that can occur. So they must add up to equal 1, which is the 100% of the outcomes. So now we have somebody making a position here. Carla says that the probability model is incorrect since everyone in the class did not end up with 2 correct guesses Sorry, I skipped a page, forgot there's this backside. So now I'm on page 910. I'm sorry, 911. So Tristan claims the model is also complete because the probabilities for all outcomes are equivalent to each other. All of them were 0.2. George disagrees and says the sum of all the probabilities is 1, but that doesn't mean the probabilities of each outcome is always equivalent to the other outcomes. Who's correct, and explain? Well, in this case, George is correct. Remember that in some sample spaces, some outcomes are more likely than others. For example, when we did the sum of rolling 2 dice, it's more likely to roll a sum of 7. I could have rolled a 6 first and a 1 second, or a 1 first and a 6 second. 2 and 5 or 5 and 2, 3 and 4, 4 and 3. But rolling a sum of 2, I could only get one way. I'd have to roll a 1 with both dice. So it doesn't have anything to do with a probability model. A probability model, just all the outcomes has to equal 1. Now, a uniform probability model occurs when all the probabilities in a probability model are equally likely to occur. So if all the numbers are the same, it's called a uniform model. Assuming you do not know the answers to the 5-choice multiple choice question, each answer choice has the same probability. So this is like the example we just did where we got 1/5 for everything or 0.2 for everything. When the probabilities in a probability model are not equivalent to each other, it's called a non-uniform probability model, and that would have been like this question up here. And another example of a non-uniform would be a weather forecast that states that there's a 30% chance of rain. That means there's a 70% chance of not raining. The sum of the two probabilities is 1, but the outcomes don't have the same probability. One had a 30%, one had a 70%. So suppose the correct answer to a multiple choice question is C. Simulate answering the multiple choice question by randomly selecting an answer choice 10 times. Write each answer choice on a piece of paper. Make sure all pieces of paper are the same size and record. So I already had done this with the class. We took little pieces of paper, we wrote A, B, C, D, and E on them. We folded them up, we tossed them in the middle, mixed them up, randomly selected one, and the kids kept track of how many times they got a C. So this was the average from the class. There were 2 kids that did not get a C at all out of 10 times. There were 4 that got 1 C. There were a bunch that got 2, 3, and 4. So this was experimental. This was based on an experiment we conducted. So remember that the theoretical probability of getting a C is 1 out of 5. So if I were to have 10 questions, I could scale this up. I would predict that 2 out of the 10 questions would have an outcome of C being the correct answer. So according to my probability model, how many times should the correct answer have been guessed? So again, we know that theoretically 2 out of 10 times you should get a C, but in actuality that's not what happened for every kid. Most of the kids did get 2 C's, but at least you can see they tend to be clustered pretty close to that. Nobody had 5, 6, 7, 8, 9, 10 C's. Only one even had 4 C's. So most of them are within 1 or 2 of what the theoretical probability is. So in theory, it should be guessed 2 out of 10 times. And our experiment does sort of support that answer. Okay, now for our last question. So Carla says that the probability model is incorrect since everyone in the class didn't end up with 2 correct guesses, as shown on our dot plot. Explain to Carla why the probability model is correct. So Carla is misunderstanding theoretical and experimental. The model is correct because it gives us the theoretical probability for each outcome. When we looked at that table and we had 0.2 every time, that's in theory what should happen. However, when we conduct an experiment simulates the results. The class results are based on experimental probability. It's probably close to theoretical, but it's not always going to be exact. That's the end of the mini lesson.